Welcome guys. So in this video, I want to talk about the linear algebra basic. Yeah, but I say advanced basic is that basically if you study the physics or engineering mathematics, then usually you will not hear about the Zorn's lemma, and then you will not your understanding for basis is somehow like very I should say still correct, but not fully understand. So in this video, I will I will say the I will say some basics of vector space in the linear algebra, which is seldom mentioned. Okay, so what important is that we will use set theory technique, or basically the Zorn's lemma. So I will not prove Zorn's lemma here, but I will use Zorn's lemma to show that every vector space has a basis. Okay, so remember that if you know, so if you know the basis, vector space has a basis, then you can start write a matrix, right? Because the matrix is just some formation in the basis, right? So every vector space has a basis. So I would say it's the heart of the linear algebra. And basically, this heart of linear algebra cannot be easily derived from the axiom of vector space, right? So let's talk about one definition of the vector space. So one definition of the vector space is that you use 10 axiom, right? So let's say that a plus 0 is a, or a plus b is b plus a, right? There are 10 of them. So basically, you have addition and then multiplication of the field. So the field usually choose to be a real number, a complex number. Or if you okay, then you can use finite field. But there is a second definition that is like a more abstract algebra. So I can define a vector space to be let's see. So yeah, so I can define a so the division ring, right? So the division ring is defined to be the commutative ring with identity, but so any not commutative, a ring with identity, but a non-zero element has inverse. Okay, so for example, the quaternion is a division ring. Okay, so I can define a vector space as the unito module over a division ring. Okay, so this is the more general definition than the powerful than your linear algebra course. But actually, the basis and other ideas can be generalized into this kind of vector space. So basically, what generalization is that my original field is replaced with the division ring. If you add the commutative property, then the division ring becomes field. Okay, so one important thing I want to prove now is that let's call it lemma. This lemma says that if X is a linear independent subset of let's say V, you have vector space, and if you pick Y is not in X, Y in V not in X, and then X union Y is linear independent if and only if Y is not Y is not linear combination of X, or basically Y is not in span X. Okay, span X. So span X means that you take linear combination of vector in X. And a linear independent, I think I don't have to explain. Linear independent means that if your linear combination vector, linear combination is 0, then each coefficient is 0, right? So this lemma is also important, but people not general. So people usually use it, but hard to remember the proof. Okay, but so the proof is trivial, right? So if you start from here, that I can assume that X union Y is linear independent. but I suppose the convert. I suppose this statement is false. So this statement is false. Then from here that y would be span x, right? But if y is in a span x, then x union y will not be linear independent, right? So this is trivial. Okay, so second direction is that if y is not in span x, then I need to show that x union y is linear independent. So let's say this is x1 up to xn. Actually, it can be infinite, right? But we only take the finite of them. And then I ask about ci xi I from 1 to n plus cn xn, which is 0. And that's I first I claim that the cn must be 0, right? The reason is that if cn is non-zero, then you can write xn into minus negative cn or something, right? So then this is not xn, this is y. Sorry. So I claim y I claim this cy is 0. At least c is 0. The coefficient before y is 0. And the reason is that if it's non-zero, then y will be linear combination of summation ci xi, right? So which tell you that c must be 0. If c is 0, then all ci will be 0, right? Because I already assumed that x is a linear independent. Okay, so now we have a proof. So this proof tell you that if you have a x, right, in a vector space V, then if you take any y which is not linear, which is not in a span x, and you put in, then they will form a larger linear independent set. Okay, so from here that we can prove every vector space has a basis. Okay, so the proof idea is so let's explain. So basis means that a set of linear independent vectors, let's say x, and their span x will be whole V. Okay. And the proof is basically use the Zorn's lemma. So Zorn's lemma tell you that every partial order set. So if every partial order set, basically you have a set which endorsed with partial order. So if every partial order set has a upper bound, then there is a maximum element. There is a maximum. I should say maximal element. Okay, so in order to use it, we need to create a partial order in the vector space, right? So it's very easy that I claim my. So let's say my partial order is that if A is if you have a set of vectors and you have B a set of vectors, if A is subset of B, then I denote that A less or equal to B. So easy to check that this is partial order. And every partial order chain, right, has an upper bound, means that obviously if you have A1 subset A2, A3, which are all linear independent subset, then there's an upper bound, right? Because the upper bound can take to be V. You can the upper bound can take all the union. Okay, so all the union will be still linear independent, and there is an upper bound of chain. So by Zorn's lemma, there's a maximum element. So let's call a maximum element. Let's call a maximum element X. So X is a set of vectors, and by definition, I define the order only for linear independent, right? So by definition, X is already linear independent, and I define a span X. I can compute a span X. Then I claim this maximum element span X will be V. Okay, and the reason is that if not, then by the lemma, I can take y belongs to Vx, then which is linear independent in X, and I put it. And it's still linear independent, so which violates the maximum, which violates X is a maximum. So basically, this Zorn's lemma idea just tell you that suppose you have a vector space V, right, and you take a vector, you compute span. If this span is not V, then you take another vector, put it, and you span. If it's still not V, then you put another vector and you span, and you keep going, right? And from set theory results will give you infinite deduction. If V has infinite dimension, then you finally will exalt this V. So this is the idea. But the set theory results tell you that in the mathematically how to use a set theory to tell you that this infinite process is logical correct. Okay. Yeah, and there's another lemma which is easy. So once so there's a proposition. I think this proposition is trivial. So if V has if Y is a subset of vector space and span Y equals to V, and X is a subset of Y. So basically, you have this. Then there is a basis B such that X be Y. Okay. So basically, these tell you that if you have vector space V and you have some vector Y generate V, right? And also you have some subset X. Then you can you can put some basis, right? You can add some basis to make this one, this guy from, oh, by the way. So X must be linear independent. So if you take any linear independent subset of any subset of vectors, then you can add an additional basis to phones to make you phones basis. Okay, so this is the proposition which, if you notice, then you can use this to prove the rank numerality theorem. Okay, so actually the rank numerality theorem is not difficult if you, I mean, if you actually learn the basis of all the basic of the abstract, I mean, this type of linear algebra, right? So the proof is basically using using a previous idea, right? So if you take X, right, and then you add you add another one. So you start from X and you add another B, you add another vector which is V delete X. And if it's still not linear independent, then you keep going, right? And I already say span Y equals to V, so you can always find enough vector in Y such that I span V. Okay. And there's let's talk about next. And the next is also interesting, which people usually use it, but they don't know why. It's the proof is it's seldom to mention. So let V is a vector space and XY be a basis. So you have two bases of V. And for every X belongs to X, there exists Y belongs to Y. Oh, such that X delete X union Y is a basis. So this is called exchange lemma. Okay, so this is say you have a set of X, you have a set of Y, right? And then you pick out any X, then you can delete X and find some stupid Y, and you put Y in, then still be a basis, right? So basically, you can exchange a vector, and this is commonly intuitively, right? Suppose you're in two dimensions, your basis is these two, and then there's a guy, his basis is these two, right? And then you can delete this, and maybe you add at least one. Let's still be a basis, right? So I mean, for each X in X, you can always find a Y such that you delete that X and add some Y as a basis. Yeah, so this is the intuitive correct. Okay. Okay, so let's see a proof. So the proof is basically if X belongs to Y, then it's okay, right? Because if X belongs to Y, then I can delete X and add X back. So this is a trivial. Okay. Okay, so let's assume that your X, the X you pick is not in Y, and you can use S to be a basis, right? You can S to be a span of span of X delete X. Okay, so you do this, right? And obviously that obviously if Y is a subset of S, if Y is a subset of S, right, then I already know span Y will be V, right? Then span S will be V. But this is impossible, right? The reason is that if you span SV, that means you delete X and you still get X, right? So that means this X is not linear independent in X. So, but I already say it's basis, so it's linear independent. So this is impossible. So the only case must be Y is not in X. Y is not totally in S, right? So that means you can find the Y, which is not linear independent. Oh, sorry, which is not a linear combination. So not a linear combination of S, right? Then by definition, then by my previous lemma tell you that if you start from S and the union such Y will be linear independent, right? So I can take, so it means I take some X out and I add some Y, which is still be which is still linear, is a linear independent. Okay. So your S, you delete this and add some Y will be linear independent. So finally, I need to show that this will generate V. Okay. Yeah. So let's maybe write down. So X delete X union Y. Let's call it X prime. Okay. Okay. And I know that this so I already know that this X prime is a linear independent set, right? Okay, so let's see. So now I claim what? I claim X is in a span list. Okay, so the idea is that I already delete X, right? So it's not guaranteed that I delete X and I add less such Y to be linear independent set such that this originally small X will be in the linear independent, will be the span of, because I already kill one, right? Kill one. So in order to show this span V, you need to show that X will be span will sit inside this. Okay, but by definition, right? By definition, so let's see how to prove this. Okay, so suppose not. Right, suppose not. Then your X prime, you can suppose not, right? Suppose X is not in, then your X prime union list will be another linear independent set, right? But the X prime union X will just be X union Y. Your originally larger set X union Y. Okay, but now this is still, but now so now you have a linear, you say that X union Y is a linear independent set, but the problem is that X is a basis, right? So Y is a linear combination. Y must be span X. So this set cannot be linear independent. Cannot be linear independent. So which is a contradiction. Right. So from this, so this means that since X is a basis, right? So Y will be spanning X, right? But this fact will contradiction that I say this set is a linear independent set. Okay, so contradiction. So that means we prove this exchange lemma. Okay. Okay, so the final fact that usually people always also use is that all basis of vector space has the same number of elements. So this just tells you that the dimension is an invariant quantity of the vector space. So let's say if you have 3 dimensions, then you always need 3 vectors, 3 bases, right? This is somehow intuitive trivial, but actually you need to have a Zorn's lemma and the other that's this kind of previous abstract idea, then you can prove it. Okay. So prove. So the proof is that by exchange lemma, right? By exchange lemma. So the idea that things you can exchange, right? So exchange lemma tell you that I have X and I have Y, and then for each X, remember for each X, right? I can delete this and pick up some of Y and put it, right? And so by definition, you can keep going, right? You can pick another X and pick some Y, and you add it. You replace this X and replace some Y, and keep going, right? So in order to do this, the number of Y element must greater than X, right? So X must greater than the set of X must less or equal to Y, right? But this is symmetric, because you can start pick Y and replace X. So Y is less or equal to X, so X must Y. Okay, so proof. Yeah, so this I remember that. So I think these are all the important. So these are all the important results that that we need to use. Okay, so let's people say, so final proposition is that if S is a subspace of V and the dimension of S. So dimension of S means that you can pick S as a basis. You ask how many bases. Dimension of if dimension S is dimension V, then S must be V. And this proof is trivial by exchange lemma. Okay. Like I mean you can show this, right? Because yeah, okay. Okay, so that's it. So yeah, see you guys. I mean, this is just I think it's in start if one need to start prove some important if one need to start proving some important theory in a linear algebra, then the basis the basic of this the basic of this basis and this idea need to be sharpened. So that's why I make this video. Okay, so see you guys in next video.